Now that we have a better understanding of how neural networks are structured and some of the considerations needed in training them, this video will introduce recurrent neural networks as a popular variant of neural network model. Recurrent networks are specialized for modeling sequential and time series data. Particularly in education contexts, we often come across examples of sequential data. If we were given this sequence of correctness values for problems in an assignment, for example, we may want to determine whether the student learned the concept as part of our model. If we wanted to use this sequence to predict whether or not the student answered the next problem correctly, we would need a way of incorporating the full sequence of values into that model. We would need a way of featureizing that. One way to handle this is through feature engineering. We can use aggregates of these values over certain time periods, for example, to describe the sequence. Regardless of the length of the sequence, we could divide it in half and calculate the average performance in the first half and the average performance in the second half as two distinct predictors to be included into our model. We could even further derive additional features from these to describe their relationship, such as taking the difference to calculate a rough estimate of whether or not learning occurred. But what are the right set of sequential features to calculate here becomes an important question. It may not be clear as to how we should split our sequence or how far back in the sequence we should attend to. Remember that one of the benefits of neural networks is that they help to automatically generate features from raw data. So if we had a neural network that was able to attend to sequential patterns, we wouldn't need to worry about handcrafting these sequential features. Recurrent neural networks do exactly this. So given a sequence of time steps, or sequence steps, that is a set of samples that belong to an ordered sequence, the model effectively learns sets of weights that connect not only the layers within the network, but also weights that connect to earlier outputs of the network from previous time steps in the sequence. In other words, a recurrent layer in a neural network will pass its output onto the next layer in the network, as well as to the model in the next time step. So recurrent networks are just neural networks that utilize at least one recurrent layer. Just as we have layers that propagate data to subsequent layers in the network, there are other types of layers that we may incorporate. It is also the case that we may include multiple recurrent layers to represent nonlinear time sequences, or combine recurrent layers with other layer types for certain advantages. So among these, there are multiple different variants of recurrent layer, with a recurrent neural network layer being the most simple. An RNN, or recurrent neural network, incorporates an RNN node, this recurrent node, which applies a tanh function to not only the inputs from the preceding layer, so it's like an activation function in that way, but it also applies it to the output of the layer in the previous time step before then propagating this onto the next layer. So again, we can think of recurrent models as just being connected in terms of the preceding layers, but also connected to themselves in previous time steps so that they are passing on new information or previous information with each time step within that model. The output of the model is dependent on the current information being passed to it from the current time step, as well as some past information that has been aggregated over the course of the sequence. Long short-term memory, or LSTM, networks are another common variant of recurrent model. LSTMs incorporate a more complex node structure that includes memory. So the LSTM node itself acts almost like a small neural network, incorporating a set of gates which affect the flow of data through the layer. Essentially, this can be simplified to say that the LSTM first determines how much of its own memory it should forget when it's being approached within the model. It then determines how much of the new information from the current time step it should add to its aggregated memory. And then it determines how to combine the new information with the aggregated memory to form an output that is then propagated to the next layer. Training recurrent neural networks is done much in the same way as any other non-recurrent network, with some there are a few also additional considerations. While these models can handle sequences of varying length, it is common practice to use padding as a way of making all of the training sequences the same length. Padding is just the process of adding placeholder values at the beginning or end of the sequence such that all of the samples are then made to be the same length. This is typically then paired with a masking sequence that can be supplied to the model to inform it to not use any of the padded values for updating its weights. And it's also important to note, however, that this practice is usually done for greater efficiency of model training as opposed to having any real benefit to the model's predictive performance. So this is more of a practicality aspect than it is a benefit to model training. It's also important to remember that each time step in the sequence may be represented with any number of features describing that individual sample. So just as we would have a set of features describing samples for other models, we can similarly have any number of features or predictors representing each time step. The sequence then becomes an additional dimension for the model. So rather than representing our data as simply sets of rows and columns, we are also able to, we would need to represent this kind of third dimension of time as an additional component in these models. So for this reason, it can sometimes make data a little bit harder to work with when we want to use them in these recurrent networks. However, there are a number of tools out there that have made this process a little bit easier.